All right, so in this week's lecture, we're going to be looking at the conditional, which is kind of the main topic of study in sections 3.3 and 3.4 in our parent class. And kind of like last week, and really for everything that we cover in chapter 3 in the parent class, there's not really any direct mathematical prerequisites that help with this material. Just because it's very different from the kind of math you would have seen before. It doesn't really fall into the category of math even. It's symbolic logic, which is related. But so because of that, I think it's better to use our time this week to practice what we're already doing in the parent class and just get a little bit more under our belts so that we can kind of hopefully, grasp this material a little bit better. So we're going to be just looking at a few different types of problems that we deal with in the parent class when talking about the conditional. Let's start with this first set of instructions here. It says, let P be the statement 5 plus 6 equals 7. Q be the statement 5 plus negative 5 equals 0. And R be the statement 1 equals 2. Determine the truth values of the following statements. And we have two problems to work out using P, Q, and R the way they're defined above. So these are our mathematical statements, and they are either true or false. And we can determine their truth or falseness. We can determine their truth values pretty easily just by looking at what they say. So P, 5 plus 6 equals 7, is obviously false because 5 plus 6 is not 7. Okay? Q is true because any number plus its opposite is always equal to 0. 5 plus negative 5 must be 0. R is also clearly false. We know that 1 is not equal to 2. So what we have here are two false statements and one true statement. As we saw in the parent class, when we look at a compound statement involving statements like P, Q, and R, as we defined above, where we know their truth values, we can use that knowledge to determine the truth value of this more complicated compound statement here. So I begin by replacing the symbols that I'm seeing, P, not Q, and not R specifically, with their corresponding truth value. So again, we decided up here that P was false. So P I'm going to write as capital F, which is its truth value, implies, that's how I read the conditional, I read that arrow as implies. So false implies what? Well, not Q. Remember, Q we decided was true because 5 plus negative 5 is 0, which means not Q would be false, okay? And, it's my conjunction there, not R. Well, R was a false statement, so not R would then be a true statement. Remember, negations always have the opposite truth value of whatever statement they're negating. Now, as we saw in the parent class, from here we go through sort of a simplification process, usually, well not usually, pretty much always working from the inside of parentheses first, kind of like order of operations in arithmetic, and we kind of try to get this whole thing simplified down to a single truth value, either true or false. But one thing that's kind of nice about the conditional is when we have an antecedent that's false. Remember, in a conditional, we call the statement that shows up, well, I'll use this. The P here, the statement that shows up to the left of our arrow is called the antecedent, and the statement to the right is called the consequent. If the antecedent is false, then it does not matter what the consequent is. It can be either true or false over here, and we still end up with a true conditional. And this is one of those things that, again, is difficult to wrap your mind around because it doesn't seem like false implies anything should be true. But the way that we define the conditional, this will always happen. And so we can knock out problems like this pretty quickly as soon as we see that our antecedent is in fact true, or false, sorry. Moving on to this one. Slightly more complicated, but it is a conditional because it has that arrow right there. So this one says not P or R, in parentheses, implies P and not Q, also in parentheses. So remember, we always start with in parentheses first, but, well, actually, sorry, let me back that up a step. I'm actually just going to replace each statement, each component statement with its truth value. So P was, again, a false statement, which means not P must be a true statement. So here what we have is true, or R was a false statement, so true or false is what I have written here. Implies what? P and not Q. So P is false. So I'm going to put false here. And not Q. Q was true, so not Q must also be false. All right. Now, I want to work within these sets of parentheses. This is a disjunction. We think of that as the word or. And remember, anytime you have a disjunction, the whole thing will be true just so long as one or both of its component statements are true. In this case, one of my component statements are true, so the entire disjunction is also true. Over here, I have false and false. This is a conjunction. Remember, conjunctions are only ever true when both component statements are true. In this case, neither of them are, so this is actually going to be false. True implies false. And then here we have the one situation where a conditional can come out to be false. So this is false. Okay? All right, so that's enough practice on that. Now we want to move on to something else that we deal with when talking about the conditional, and that's circuits. Okay? So we introduced circuits in the parent class, and again, all we're doing here is practicing these. These can be a little bit tricky for people, but what we're going to do is we are going to, excuse me, use this equivalence here. So we talked about this in the parent class. The conditional is actually equivalent to a type of disjunction. In other words, we can think of it in terms of a disjunction. So P implies Q. This conditional is logically equivalent to not P or Q. And we proved that. We showed why that was the case in the parent class. You can do that using truth tables. So for these conditionals, if I want to create a circuit, I couldn't think of the word for some reason. I want to start by rewriting this conditional using this equivalent statement. So what this says is P implies Q, P being the antecedent in this conditional statement. So in my example here, my antecedent is a tad more complicated looking. It's not just P or Q or something like that. It's P or Q. And to rewrite this, I need to take the negation of that entire antecedent. So that's going to look like this. Not, then in parentheses, P or Q. And then my conditional, this thing, is going to change into a disjunction. It's going to become or. So instead of implies Q, we write or Q. So or, and instead of Q, in this example, my antecedent is not P. So that's going to look like not P. Okay? Now, in order to effectively write the circuit, it's not going to be enough to leave it in this form. This is where we use Demorgan's laws, which we also talked about in the parent class. And remember, Demorgan's laws tells you how to deal with the negation of either a disjunction or a conjunction. So we're combining two logical connectives here, a negation with either a disjunction or a conjunction. In this case, it's a disjunction. The way I like to think of De Morgan's laws is like a weird version of the distributive property from algebra. I want to think of this negation as distributing into the P and the Q so that I end up with a not P and a not Q, but then it does something a little unexpected and it changes the kind of connective that I have here. My disjunction becomes a conjunction. And again, we showed why I think one of De Morgan's laws is true, but that's what's going to happen here. Okay? Now this disjunction here is going to stay put, so I have or not P. Okay? Excuse me. And I could put parentheses around this first one, but it doesn't turn out to really be necessary. Actually, you know what? I think I will. I'll keep the parentheses around that. It's going to help with explaining the next part. Okay? So the way I want to look at this now is as a disjunction where one of my component statements has a conjunction in it. So the way that we deal with circuits is we, again, think of it as kind of having a starting point, and then we have some paths that lead to an ending point. And we use the term series and parallel circuits in the parent class. Series circuits are how we describe conjunctions. Parallel circuits are how we describe conjunctions. So I'm going to actually start from outside the parentheses here and think of this as a disjunction of this statement and this statement. Because there's a disjunction, we're going to have a parallel circuit. That means it splits like this. Okay? Now, it doesn't really matter which one goes on top, which one goes on the bottom, but I'm going to put the first statement on top. The first statement belongs on the top part of this parallel circuit, but that statement by itself is a conjunction. Conjunctions look like series circuits, one switch or one gate after another. So I'm going to have a switch right here, and that's going to be the not P that's showing up. And then I'm going to have a second switch right after that, representing the not Q that's showing up there. Okay? And so that's going to be the top part of my circuit. The bottom part of the circuit is going to be the other statement in the original disjunction that we were talking about, and that one is simpler. It only has one component. It has the not P there. So it's going to look like this. Not P. Okay? That's what that circuit would look like. Now, we talked about in the parent class how to interpret these circuits. Basically, different truth values for P and Q will determine whether these switches are open or closed. And then if we can close enough switches using the different choices of truth values for P and Q, such that it creates a path from this starting point to this ending point, then that would be the right combination of truth values for P and Q that would make the entire compound statement true. I'm not going to delve too deeply into that right now. I just want to focus on how to sketch these circuits. Okay, so this one is similar, and we're going to do basically the same thing as the last. We're going to rewrite our conditional in the form of this equivalent disjunction. So I'm looking at not P or Q, where P is my antecedent, Q is my consequent. In other words, I take the negation of my antecedent, which in this example is this more complicated statement. So that looks like this. Not, then in parentheses, not P or not Q. And that arrow is going to change to a disjunction, and the consequent, Q, I'm not taking the negation of. It's just the same thing that I already have written there. P and R. Okay. Now what I need to do is use Demorgan's laws to bring this negation in. So again, we think of this negation as being distributed to each component statement. But remember, the negation of a negation, we kind of think of that as canceling out. So the negation of P is just P. That becomes P or, and then similarly Q. And actually, I'm sorry, I forgot to switch my or to an and. Remember, Demorgan's law will change that connective. So I caught myself there. All right, and then nothing else is really changing. So now we can write our circuit out. Once again, I have a disjunction of two statements that are relatively complicated. So it's going to also look like a parallel circuit. Okay. Now the circuit I'm going to put on top, or the part of the circuit that I'm going to put on top, I'm going to choose to be this first statement, P and Q. Because it's a disjunction, it's going to have a series circuit. So just like before, this is going to look like P this time, and Q here. Okay. Down here, I'm going to look at my second statement in this overall disjunction, P and R. It's another conjunction, so it requires another series circuit. So that's going to look like P and R, like this. Okay? And that's what that circuit would look like. When I've taught this class before and covered this section, the circuits seem to be something that people get hung up on and have a hard time with. So hopefully this extra practice is going to help you in the parent class when you're working through these kinds of problems. Alrighty, last thing I want to do is talk about those statements that we covered, I think, in section 3.4 that are related to the conditional. The converse, inverse, contrapositive, and contrapositive. So those three related statements. So let's start by reading this statement, and then we're going to write out the converse, inverse, and contrapositive of this statement. Ignore that little thing. I made a mistake right there. So it says, if I can't find my glasses, then we can't go to the concert. So in this case, this first statement here is my antecedent. I'm going to call that P. It's the statement, and actually, it's not even this part. It's everything after the if, but before the comma. Okay, I can't find my glasses. That's P. Sorry, smudged that. This part, then we can't go to the concert, is my consequent. I'm going to think of that as Q. So the converse. Remember, if you have a statement of the form P implies Q, the converse switches P and Q. So converse looks like Q implies P. Okay, so down here I'm going to write my converse. If, now I take Q and make that my antecedent now. If we can't go to the concert, then P, I can't find my glasses. Okay, that's what the converse would be. And one thing I want to actually let's talk about this at the end. Inverse is the next one. Inverse does not switch P and Q, but it negates both of them. It becomes not P implies not Q. Inverse. So the inverse keeps P and Q where they are, but then it negates them. So what is the negation of I can't find my glasses? Well, the negation would be I can find my glasses. The can't becomes a can. So if I can find my glasses, then what does not Q look like? Well, Q also has the word can't in it. We can't go to the concert. So that would mean that the negation of that would logically be can go to the concert. Then we can go to the concert. Okay? Finally, contrapositive. The contrapositive does basically a combination of the converse and the inverse. It switches P and Q, but then it also negates them. So it becomes not Q implies not P. So in this case, we just found what the negation of those two statements look like in order to do the inverse. I'm just switching their order now. It says if we can go to the concert, then I can find my glasses. Okay, so that's how those would look given the original statement. The only thing I wanted to mention before wrapping this up is just to kind of reiterate which of these statements are equivalent. So we showed in the parent class and talked about in the parent class that the converse of a statement is not equivalent to the original statement. Now, in symbolic logic, when we're just working with the symbols and truth tables, it's not hard to see that. But in kind of informal discussion with people and debate and arguments and things like that, it's a common mistake to assume that the converse of a statement is true. So in this example, we can kind of just intuitively see why the converse wouldn't be true. Let's go back to the original statement for a second. If I can't find my glasses, then we can't go to the concert. I'm going to add a little context to that to help it kind of make sense. So it sounds like if whoever is making the statement, if they can't find their glasses, let's assume that they're the ones driving to the concert. They need their glasses in order to see, and they need to be able to see in order to drive. So that might be the reason why this statement is being made in the first place. If I can't find my glasses, then I'm not able to drive, and we're going to have to miss the concert because now we can't get there. That kind of a thing. Okay? The converse of that statement does not necessarily make sense. So once again, the converse says, if we can't go to the concert, then I can't find my glasses. So it's not hard to see why the first statement implies the second, but it's not necessarily true that the second statement implies the first. Remember, if we can't go to the concert, so here we're thinking of that as an assumption. I'm assuming that I cannot go to this concert. Does that necessarily mean that I couldn't find my glasses? Not necessarily. That could be the case, but there could be other reasons why we weren't able to go to the concert. Maybe it was canceled. Maybe the artists who were supposed to be performing in this concert had their van break down and they weren't able to make it. There's other reasons why we could have missed this concert. So this assumption does not necessarily imply this conclusion, even though when we switch them around, P did imply Q. So I bring that up again just because it's a common logical fallacy that people make to assume that if a conditional statement is true, then its converse is also true. But that's generally not the case. The contrapositive, however, is equivalent to the original statement. If the original statement is true, the contrapositive will also be true and vice versa. But that's kind of all I wanted to say on that. So that's going to wrap things up for this week.